Hi there. Um, I really apologize for the previous problem, but I have got it figured out, and I know you're not in class anymore, and you probably don't care, but I did send you a list of formulas, and so I'm not going to rewrite all those formulas down, but I do want you to notice that the centripetal acceleration formula is usually being provided by the gravitational formula. So I wanted to just point out a couple things for especially those of you who weren't in class last year. If you are standing on top of the planet, beautiful, nice planet there. If you're standing on the planet, again, we measure from the middle of your mass to the middle of the planet's mass. And so that's the distance. But if you're really standing on top of a planet, then this distance, of course, is insignificant. But this distance is the radius of the planet. That's why in the first equation it was d, and in the second equation it's r. Because if you're standing here on the planet, then the planet radius is really essentially the distance between the center of your mass and the center of its mass. The reason we got that second equation is if we start off with the gravitational force, and again that is F times g. No, that is not F times g. That is the gravitational force, just like we have an FA and an FF and all the others. It's not F times g. So anyway, Fg is equal to gm1 m2 over d squared. Now, this was Newton's rule of universal gravitation, and that worked out fine. But the reason, if you're standing here on the planet like in this picture here, the force that develops here is your weight. So the gravitational force between you and the planet is your weight, and we know W, of course, equals mg. Well, if mg is equal to gm1 m2 over d squared, then we say, hey, this is your mass, and if I cross out your mass over here, what's left is the mass of the Earth. And again, that distance is the radius. That's how we end up with g prime is equal to the gme over r squared equation. So that's where that idea came from. Now, this works so that you can find the acceleration due to gravity anywhere on the Earth, or anywhere in the universe, excuse me. You could do this on the moon or on the sun or anywhere else you wanted to. But again, that gravitational acceleration is oftentimes providing the centripetal acceleration. So if the Earth is here and you're in orbit around it like this, then of course the radius is both the planet radius plus what distance am I above the planet radius. These two combined would be the r that plugs into here. But if you're in orbit around a planet, what is pulling you in the whole time, providing that centripetal acceleration, is that acceleration due to gravity. So the acceleration due to gravity is pulling in all the time. Now, if this is the Earth and the Earth is spinning around, because it does that, that's why we have day and night, it takes, of course, 24 hours to rotate one time. Now, if I put a satellite in orbit so that it also takes 24 hours to go around one time, then that is what's known as geosynchronous orbit. Geosynchronous, geo means the Earth, synchronous, C-Y-N-C-H-ronous. So geosynchronous means synchronized with the Earth. So what that means is if the Earth takes 24 hours to go around and your orbit took 24 hours to go around, then that means no matter where you look up, wherever up is for you, that's where that satellite is the whole time. So the satellite stays in the exact same spot. We use geosynchronous orbit really for putting a lot of satellites in orbit, and those are nice because I can set up my big satellite dish that has a little thing on it, and it is directed straight toward a satellite that's super duper far out in space that's in geosynchronous orbit. And that way, if I'm in near Earth orbit here, then it's traveling much, much faster than this, and my satellite dish would have to move. But if I can just point my satellite dish at one spot and leave it there the whole time, that's there because that thing I'm pointing at is in geosynchronous orbit. So hopefully that makes a little bit more sense. But anyway, since my AC is being provided for by g prime, then I can put the equations together. I can say, like, say 4 pi squared r over t squared is equal to the big G m e over r squared. And I can use this to solve for all sorts of things, and especially if I know the t. If I know the t is geosynchronous, then I know it's already 24 hours, but I have to convert that into seconds before I plug it in here. So that's about the trickiest part that goes along with that stuff. So that should help on that problem, at least somewhat. So now I would like to clear this and go back into the other type of problem. Now the other type of problem was what happens when I have a meter stick that's hooked up. We're going to actually do this lab next week. But let's say if this is my meter stick, at point 10 I hang a weight, and at point 20 I have a string going up, and at say 35 I have another weight, and then at 65, just to keep the numbers simpler, I'm going to have a weight, and then at 80 I'm going to have another string going up, and say at 90 I'm going to have another weight. Now let's pretend that this weight is 1, and this weight is 1.5, and this weight is 2, and this weight is 3. Let's say our meter stick is a really fat meter stick that is also 0.5. Now these are all kilograms. So if this is the case, then I want to know, well, what tension must be in those strings. We're going to call this string A, and this is going to be string B. Now, in reality, what we're going to do is string A and string B are going to go over a little pulley, and we're going to hang weights on the other side that's going to balance it out. Now, if it's balanced out perfectly, what's going to happen is, of course, the total force going up is going to equal the total force going down. Well, the total force going up, of course, is just A plus B. The total force going down, of course, is all the other weights. Now, the other weights, of course, are going to be 1 plus the 1.5 plus the 2 plus the 3 plus the weight of the ruler itself, which is 0.5. So that's going to be a total of what? 1, 2, 3, 4, 5, 6, 7, 8. So that's going to be a total of 8 kilograms going down, which means we know A and B going up has to also equal 8 kilograms. So we got that much mentally going for us. Now, that part's super duper easy. Nobody's going to have trouble with that. Here's the second part. We are in equilibrium as far as up and down motion goes, but we're also going to be in equilibrium with regard to torque. So the total torque going clockwise and the total torque going counterclockwise are going to have to equal each other. They're going to balance out. And you're saying, well, okay, I remember you talking about torque, and I remember that torque equals force times distance, and the force and the distance, of course, were perpendicular to each other, so we've got that. Now, if torque equals force times perpendicular distance, if we are in equilibrium, then we're not torquing any direction, and so you say, well, what's the pivot point? How do I know where it's going to pivot? Well, the fact of the matter is we could make it pivot anywhere we want. We can call anything the pivot point. It could be the end of the ruler, it could be the middle of the ruler, it could be any point we want, but think about it logically. I have two unknowns. I have A and I have B. In the example on the right, the translational part, just the up and down, I cannot figure out what A and B are. I know what A and B together are. They're 8, but I don't know what the total is. So how do I figure that out? I can't. I can figure it out with the torques though. But since I have two unknowns makes things difficult. So let's make it only one unknown. Well, how do I make it only one unknown? Well, really simple. All I have to do is pick one of my points, A or B, and call that my pivot point. So if I call A the pivot point, if this is my pivot point is right at 20, then what is the distance to point A? Well, the distance to A is 0, so if it's 0, then that means the torque at that point is 0. So if the torque at point A is 0, torque due to the string at A is 0, then that is no longer a factor in my problem. So if I look at the first one, this is over on this side of my pivot point, so that's going to cause me to torque that way, counterclockwise. On the other hand, all the other weights are on this side, which means this weight wants it to run this way, this way wants it to run this way, and this way wants it to run this way also. They're all trying to torque me clockwise. Now you say, well, what do I do with the mass of the ruler? Well, the mass of the ruler, really, we could just pretend that the mass of the ruler is a mass that's hanging right at the midpoint of the ruler. And so now this becomes, I can get rid of this and just pretend that the ruler is now massless and there's a little extra mass, which also is going to be going clockwise. So I say to myself, hey, this is great. I know that my total counterclockwise has to equal my total clockwise. And then I say, wait a minute, this can't possibly work because I've got 4 things over here that are clockwise and I only have 1 thing here that's counterclockwise. No, there's 2 things that are counterclockwise. The other thing is string B. String B, pulling up on this point, is going to cause it to be a counterclockwise torque. So again, since torque is force times distance, then if we look at this first one and B together, these 2 together should balance out these 4. So the equation we get is really quite simple. I have 1 times its distance plus B times its distance is going to equal all of the others. So I have 1.5 times its distance, and I have 0.5 times its distance, and I have 2 times its distance, and I have 3 times its distance. Now, you're saying, but aren't the distances just 10 and 35 and 50 and 65? No, it's the distance again. The distance has to be measured from the pivot point. We defined our pivot point as here at 20. So yeah, this one from 20 to 10, it is in fact 10 away, but it's 10 away not because this says 10, it's 10 away because 20 minus 10 is 10. So this distance is 10. Now, how far away is B? Well, this is at 20 and B is at 80, so that's a distance of 60. Now, the 1.5 is at 35. 35 is how far from 20? That's 15 away. The 0.5 is at 50. 50 from 20 is 30 away. The 2 is at 65. 65 to 20 is 45 away. And of course, 90 over here is how far from 20? It's 70 away. So now you look at this and you say, hey, the only unknown I have now is B. So you're right. So I have 10 plus 60B equals, and I have all this mess. So I'm just going to do that in the calculator all in one big step so it's easier. 1.5 times 15 plus 0.5 times 30 plus 2 times 45 plus 3 times 70 equals, and I get 337. Where am I? 337.5. So that's the total on the right side. So of course, since 10 is plus, what we want to do is subtract that, and I'm going to get 327.5 equals 60B. And then of course, I want to divide both sides by 60, and that will go away. So I divide that out, and I find that B is approximately 5.46 kilograms. So that's how much weight we would want to hang. You know, again, we're going to have a pulley, and so we're going to hang a little mass over here, and 5.46 is going to be over there. And you say, well, how much is going to be at A? Well, again, what we could do is we could say, okay, I'm going to put my pivot point now at here and do the same process to look for A, but it's much, much simpler to just say, hey, I know A plus B equals 8. So if I know this is true, then 8 minus 5.46 is going to give me what A is equal to. So minus 8, and I get 2.54. And again, if we would do it the long way by putting the pivot point here and doing it this whole process again, we would find that A turns out to be that exact same thing. Now, if I was asking what is the tension in A and B, then we would have to take these masses and, of course, multiply them by gravity. But beyond that, that's pretty much all there is to that type of problem. They're really kind of simple. What we're saying is the total torque clockwise has to balance the total torque counterclockwise. And we pick one of our unknowns to be our pivot point because that makes its distance 0, which makes its effective torque 0. So that makes that easier. So what I want you to do is, again, you should pause this if you need to write down something that you didn't write down here. But after you're done pausing, I'm going to erase this, and I'm going to put some other values up there. And I want you to try it on your own, and then I want you to advance it and see how that goes. So here we go. So if you look at this, this is the one I want you to try now. So go ahead and pause the video and then write down all this stuff and work out the problem and figure out what A and B are. And then I will work them out and we'll see if you got the same answer I did. So, ready, set, okay. So now I need to redraw that one. And I totally forgot my numbers, sorry. So we got 1, 3, and 2.5 at 5, 45, and 90. Sorry, this program doesn't let me import pictures. We had 1, we had 3, we had 2.5. That was at 90. This was at 45. This was at 10. He asks, hopefully. I'll check again in a second. I also said that the meter stick, which of course its mass is going to be at its midpoint, was 0.225. So that one is here, and then we had A going up here somewhere, and we had B going up here somewhere. And let me double check on the numbers. Okay, 45, 3, 5. Okay, 5. And so we had 15 and 80. So this one was at 5. This is at 15. And this is at 80. So those are our numbers that we had. And again, if we're going to do this right, we can pick either A or B as our pivot point. Now, when you did this, you probably worked out A as your pivot point. I'm going to pick out B for our pivot point this time, just so that we're showing you that it works either direction. So if I put B as my pivot point, then I say to myself, hey, this one is going to torque me clockwise, as well as A is going to torque me clockwise. So we'll call clockwise positive. And then this one is going to be torquing me counterclockwise and a counterclockwise and counterclockwise. So they're going to be negative. So again, I'm going to have 1 at its distance plus 3 at its distance plus 0.225 at its distance is going to equal A at its distance plus the 2.5 at its distance. And then I just have to figure out what the distances are again. So if if this number 1 starts at 5 and I'm going to go all the way to 80, then that is clearly 75 away. And so if I'm at 45 here for the 3, 45 to 80 would be a change of 35. The 0.225 is at 50. 50 to 80, of course, is a total of 30. A is at 15. B is at 80. That's a change of 65. And then the 2.5 is at 90, which is 10 away from 80. So this becomes 10. So then it just becomes a matter of plugging in. So 1 times 75 is clearly going to be 75 plus 3 times 35 plus 0.225 times 30 is going to give me a nice whopping 186.75, and that's going to equal 65A plus 2.5 times 10 is clearly 25. So again, the opposite of plus is minus, so first I want to subtract 25, and 6 minus 5 is 1, 6, 165 equals 65A. So then to find A, of course, I need to divide both sides by 65, and that's going to give you 2.49. So yeah, 2.49 kilograms is what we would hang on A. And so then we say, well, how do we find what's hanging at B? And again, remember that the total, the total force going up is going to have to equal the total force going down. So the total force up is going to equal A plus B, and the total force down is going to equal all those weights. So we're going to have 1 plus 3 plus 0.225 plus 2.5. So we're going to have 1 and 3 is 4, 5, 6. So we're going to have 6.725 kilograms is the total going down. We already know that 2.49 of that is going up, so the rest of it must just be the difference between those two numbers. So minus 6.725, and I get 4.24. So B must be 4.24 kilograms. And again, you should always kind of mentally look at this and say, does this make sense? Since most of our weight was on the right side, well, this one is kind of fairly middle-ish, and this one is on the right side, which is quite a bit heavier than the left side, then that means B should be bigger than A, and that's what we see. So hopefully those were the numbers you got, and this makes a little bit more sense, and you've had a chance to practice, and you're wonderful super genius, and you can get your homework done. So hopefully that helps, and I will see you Monday. So thank you so much for your patience, and I love you guys.